Modern power systems are undergoing a fundamental transformation driven by the rapid integration of inverter-based renewable energy resources, electrification of transportation, and the proliferation of distributed generation. This shift toward inverter-dominated systems has introduced unprecedented operational challenges for transmission and distribution networks, including high ramp rates, reduced system inertia, bidirectional power flow patterns, voltage instability at the distribution level, and frequency volatility at the transmission level. Battery energy storage systems, BESS, have emerged as a critical grid infrastructure asset capable of addressing these multifaceted challenges through fast, dispatchable, and controllable power injection and absorption. Unlike conventional synchronous generation, BESS can react in milliseconds, making it ideally suited for real-time grid balancing and the provision of essential system services. The following analysis examines 6 critical questions that utility engineers, planners, system operators, and regulatory bodies must address to successfully integrate BESS into modern power systems, with particular emphasis on transmission and distribution planning, grid operations, and power system economics. The first fundamental question concerns the role of BESS in addressing distributed energy integration and managing grid load variations in inverter-dominated systems. Contemporary power systems are increasingly characterized by high penetration levels of solar photovoltaic arrays, wind turbines, electric vehicle charging infrastructure, and various forms of distributed generation. These resources introduce significant operational challenges that were not present in traditional synchronous machine-based grids. High ramp rates, rapid changes in power generation over short time periods, can occur when cloud movements affect solar output or when wind conditions change suddenly. This places stress on conventional generation resources that must ramp up or down quickly to maintain system balance. More critically, the reduced system inertia inherent in inverter-based resources means that the grid's ability to resist frequency disturbances is diminished. System inertia, provided traditionally by the rotating mass of synchronous generators, acts as a buffer against frequency changes. When this inertia is reduced, the grid becomes more susceptible to frequency excursions and potential instability. BESS addresses these challenges through multiple technical mechanisms. Time-shifting energy, achieved through peak shaving and valley filling, allows energy to be stored during periods of low demand and discharged during peak demand periods, effectively flattening the load curve and reducing the need for peaking generation capacity.